And of course, your definition of close is certainly up for debate, as is mine. But if we all agree on what close is, then we can say, hey, this tangent line, pretty good approximation for whatever curve we're dealing with. So I thought I would have you guys run through 1A first, okay? So 1A could very well have shown up on like the 1.5 to 2.3 quiz. Really, honestly, it's pretty old. So see if you remember how to do this, and if you don't, that's fine. I'll show you how to do it again. But see if you remember this. Just think of part A as good review. Find the equation of the tangent line. Oh, there's an extra of in there. Find the equation of the tangent line at the point 2 comma root 2. Ready, go. If you remember this well, this should take you, I'm going to say, 2 to 3 minutes at the most. And I'm feeling a sense of deja vu because I've asked my Algebra 1 students this question like 1,000 times. But if you're going to write the equation of a line, what are the two things you got to have? Yeah, the slope of the line and a point on the line. And don't I already have the point? In fact, if we're talking about a tangent line, we need the point of tangency, which is what that is. And we need the slope of the tangent line. And how do I find the slope of a tangent line? What am I really talking about? Yeah, in this case, f prime. So I would say that f prime of x is equal to 1/2 x to the negative 1/2. And of course, that's the slope at any point on the curve. I don't really care at all about any point. I want to know specifically about one point, and that would be when x is 2, right? Yeah. So I want to find out f prime of 2. So that would be 1/2 times 2 to the negative 1/2. So that is my slope of the tangent line. And I'll just put these together by writing point slope form, y minus root 2. And I guess this would be 1 over 2 root 2 if I simplified that exponent of to the negative 1/2. Parentheses, x minus 2. So that would be my tangent line equation. Any questions about that? Any questions about how I did the 1 over 2 root 2 or any little details? I mean,
we're still allowed to use slope-intercept.
Totally. Yeah, you can distribute and add that root 2 over and all that. You're totally welcome to do that. Any questions? Any other questions about that? Sure. So I'll just write it down here. Oops. Yeah, so negative exponent means that you can flip levels, right? You can go from top to bottom, bottom to top, as long as you change the sign of the exponent. So it would be 1/2 times 1 over 2 to the 1/2. And 2 to the 1/2 is the definition of a square root. And so that would be 1 over 2 times 1 over the square root of 2. And if you're multiplying fractions together, you just multiply your denominators and your denominators together, multiply your numerators together. So 1 times 1 is 1, 2 times root 2 is 2 root 2. Okay, anything else on that? Okay, so part B. If you haven't already looked at part B, please do try that. It says approximate f of 1.8 using the equation of the tangent line. So we've now moved off the point of tangency, right? The point of tangency was when x equals 2. Now I'm asking you, hey, let's use the tangent line to approximate the curve when x is 1.8. So we're moving off the point of tangency a little bit. Is this close enough? I don't know. That's a matter of opinion or some more complicated figurings. Think to yourself, oh my gosh, if I don't get a calculator for B, I am hopelessly lost. I would like you to look at B and say, well, hey, if I got a calculator, here's what I do. If I didn't have a calculator, I'd do this other thing. That'd be okay either way. Might take a little bit longer without the calculator, but whatever, I can do it. So I'll show you without the calculator real quick. So I'm going to take my lovely tangent line that I discovered earlier, and I'm going to write y minus root 2 minus 1 over 2 root 2, equals 1 over 2 root 2 times, now in place of x, I'm going to put 1.8, because that's the x value that I'm asked to use to get this approximation for the curve using my line. So how do you do this without a calculator? Well, 1.8 minus 2, that's negative 0.2, right? So I'm going to rewrite this as y minus root 2 equals 1 over 2 root 2 times negative 2/10. Instead of writing 0.2, I'll write what negative 0.2 really is. It's a fraction. It's negative 2/10. So when I do that, do you guys see how this 2 would cancel with that 2? Just simplifying a little bit here. So then I'd get y minus root 2 equals negative 1 over 10 root 2. Again, I'm just multiplying my fractions. When you multiply fractions, you multiply the numerators times each other, and you multiply the denominators times each other, and that's it. And then for my final step, I would say y equals negative 1 over 10 root 2, and I'll just add that root 2 over. And then this then is approximately equal to f of 1.8. Okay, and I have no idea what that is as a decimal. Anybody have that? 1.34 what? Okay, so 1.344 as a decimal approximation works for me. Okay, so we've done A, right? Lots of times. We've done B a decent number of times. C is new. So let me give you guys a little instruction on C. Is the approximation from part B too high or too low, and why? So can you imagine here, the reasoning is not going to be, well, I used my calculator, and I found out what the real answer is, and it was higher than mine, so my estimate was too low. Right? You understand? Like, that's never going to be the way the question is posed. The question is going to be posed like this. You're going to have to answer why, and it can't just be, hey, I figured out the real answer. It's going to be, I have some other reasoning. And so what we're going to typically use here, I think just about every time, for the y, is we are going to use information that we get from the second derivative. So let's review real quick. This would be good review. If I told you that the second derivative of f, so let's say f double prime was positive. If f double prime is positive, then the graph of f is concave up. The creepy smiley face, right? Okay. If I told you that f double prime was negative, then you'd say f is concave down. We're going to use those two ideas, and I'll bring in a graph maybe a little bit here too. We'll use those two ideas to help us with this. So if I'm going to be using the second derivative to tell me if my approximation is too high or too low, the first thing we probably want to have here would be the second derivative. So let's figure it out. If the first derivative is up there, my second derivative would be negative 1/4 times x to the negative 3/2. Make sense? Okay. So then there's some reasoning we could do here, I suppose. And I think maybe it would be useful to take that x to the negative 3/2 and like rewrite it using different symbols. So let's do this really quick. F double prime of x, so it would be negative 1/4 times, are you guys okay with this step if I just flip down?
So there's nothing in the like numerators.
Yeah, and that's going to be really key here, right? It's going to be super key. So then, are you guys okay with this? Negative 1/4 times 1 over square root of x cubed. Sorry, it kind of got on the crack there. So then I could come up here finally and say f double prime of x equals negative 1 over 4 times the square root of x cubed. You don't have to do all that. I just wanted to do that just so we can kind of clarify what that all means. Is that okay? Okay. So let's think this over. Just give me a little bit of reasoning. We're not going to show a lot of work. What kind of numbers could be plugged in for x? Any number. Only positive numbers. Why? You can't do the square root of a negative, right? And if I plug a negative in there, what is a negative cubed? A negative, right? Okay, so I can't plug in a negative because that would give me the square root of a negative. Could I plug in 0 for x?
No,
Why?
because the square root is 0, 0, and then you'd end up with 0 in the denominator.
Not a real answer. That's right. All right, so then I can only plug in positives for x, right? So I should picture this for a second in your mind. If I can only plug in numbers like 1, 2, 3, 4, 5, and for x, those are all positive numbers. What's a positive number cubed? positive. And what's the square root of a positive number? A positive number.
The whole
Times 4. So in other words, isn't it unavoidable that the denominator will be positive? Like the denominator will simply be positive. And then, what's a negative divided by a positive? Yeah, so couldn't I say this? That f double prime will be negative on or for the domain. I'll put that. For the domain, I'll just say for the domain of f. So whatever input you plug in there, you're going to get a negative for an output. It really doesn't matter. So yes, let's talk about this. So here we go. Some of this stuff you're not going to have to write. I'll write it out here just for sake of reasoning. If f double prime is negative, regardless of what you plug in from the domain, therefore you could say f is what? If f double prime will simply just be negative, no matter what, f will be concave down. Therefore, f is concave down. And I'm going to put down kind of an interesting interval here. F will be concave down on this interval. 1.8 to 2. Well, why would I choose 1.8 and 2 to focus on? What is 2? What is x equals 2? There's a point of tangency. Excuse me. And what's 1.8?
The approximation.
That's where I got my approximation from. So on that whole interval, from where I got my approximation from to that point of tangency, we can say that f is concave down. Therefore, if you can picture a concave down graph, I'll just sketch it out here, then I'll erase it. There's a concave down graph, right? And if I were to draw a tangent line anywhere along there, can you see how the tangent line would always be above the graph? Because the graph of f is concave down. Therefore, my approximation is too high. I'll just put that over here. So, therefore, the approximation is too high. Okay, so if you ever take a Calc 2 class, or if you ever take Calc BC, we'll start to quantify what it means to be too high or too low. We'll be like, are we close enough? And if not, what could we do to make it better and that kind of thing? Yeah.
So, wouldn't you not need to necessarily say the interval is concave down since it's just concave down forever? So
yeah, let's talk about that. You could have said, therefore, f is concave down on the whole domain of f, right?
Yeah.
You definitely could have said that. But where you're going to see this on our next example, it's going to be really important that you address the interval that matters.
Mm-hmm. If you also had just said that, like, that f is concave down at 2, wouldn't that
No, it's got to be the whole interval, because how many times could concavity change between 1.8 and 2?
But wouldn't that still be where the lines that we use to approximate?
No. So, like, what's happening at 2 is nice, but you need to be able to see the behavior over the course of the whole interval, right? Because I'll just draw this up on the board. If you say, hey, I know that at 2, f is concave down, how can you not guarantee that you don't get concave up and concave down like 4 different more times before you get to 1.8? Yeah, so just because something's happening at 2 does not guarantee anything about 1.8. And so, and here'd be the line of thinking. Because f double prime is always negative, that means that f double prime would be negative on this 1.8 to 2, right? So you do want to be in practice of mentioning the interval that we care about.
Okay.
It's definitely not just a point.
Gotcha.
Like if you said, hey, f double prime is always negative, therefore f is always concave down, therefore my approximation is too high, I'm probably going to go with that and be like, hey, she said always negative. That includes the interval. But many times the graphs we'll look at, we're going to have like concave up, concave down, concave up, concave down. Now you can't say that f double prime is always negative. You're going to have to say, well, hey, f double prime is negative on this little part, and that's the part that matters the most.
I don't understand how you said the approximation is too high.
Yeah. So check out my graph here. So what I did here is I attempted to draw a graph of f of x. And so, and you can see how this graph is concave down. Therefore, for that graph, the second derivative would be negative, right? And so what I did then is I just said, you know what? I think that a tangent line drawn anywhere on this graph, whether it's there or wherever, do you see how the tangent line, other than the point of tangency, is always above the graph? And if we use the tangent line to approximate the graph of f, the curve, then if the tangent line is always above the graph, wouldn't our approximation be higher than the actual curve?
Oh, okay.
So we're using the line to represent the curve, and if the line is always above the curve, then our approximation would be too high. But if the line was always below the curve, approximation would be too low.
Okay.
So I'm confused in part B then, why, like, how to find that 1.3?
How,
Like, does that mean anything?
we plugged it in, so that's our approximation.
Yeah.
So I would be willing to bet if we did the square root, and you're welcome to do this, if we did the square root of 1.8, it'd be pretty close to 1.344. So what we're doing here is we're using our tangent line, which we found in A, to approximate the curve.
Yeah.
How far away is too far for it to be? Like,
Well, so that's what I was saying earlier. Like if you want to start talking about like how close is close enough or how far is too far, that's a question more for a Calc 2 class or a Calc BC class. At this point, we're just going to hold off and say, well, it was too high or it was too low. Was it too high, or just a little bit too high? That's a kind of question for a different class.
So how do we assume then, like, F is concave down?
We're not assuming anything. I just proved it.
I know, but for 1.8, like, how do we know that it is concave down?
Because F double prime is negative for all the domain.
Oh,
That was that whole routine we said, hey, what could you plug in, right? You can only
Yeah.
plug in positives. What does that mean for positive cubed? And then what's the square root of that?
Gotcha.
Basically, we nailed it down. We said, you know what? There is no way that F double prime will be anything other than negative.
Yeah.
Therefore, F is always concave down on its domain.
Well, couldn't it also just not be, like, any?
That's what I said, on its domain. So I didn't write this up on the screen because I didn't have room. You guys have probably seen this graph before. This is a graph right here of y equals the square root of x. Looks like half of a parabola on its side. So this would be y equals f of x right here. And you can see how, by the graph, that's always concave down, right? So 1.8 would be like right there. 2 would maybe be right there. So I use my tangent line approximation. My tangent line would look like that roughly. So can you see how the tangent line is always a little bit above the curvy graph?
Yeah.
That's it. So basically what we did, I could explain it this way too. What we did is we found the point on the line, which was like right here. That's the point on the line. And we're using that point on the line to say, well, that's approximately the same as the point on the curve. We know we're off. The question was just, well, are we too high when we're off, or are we too low when we're off? Make sense? Question?
So can it be said that it's a rule that if your second derivative is negative or positive, we can tell if your approximation is too high or too low?
That's it. That's the connection.
Okay,
Yep, that's exactly right.
there's no exceptions, right?
Well, we're assuming continuity for sure. Other than that. Okay, anyone else? Okay, so
Down this one,
what's that?
is this concave down,
Is what concave?
like this one?
Yeah, concave down.
Fine.
Like a concave down is like an upside down bowl. Concave up is a
Yeah.
right side up bowl.
Going up, I just.
Concave up means like if you poured water into it, the water would stay. Concave down means if you poured water into it, it would just flow off.
Okay.
Something like that. Okay. All right. So you guys are going to find that number 2 is basically a repeat of number 1 with just a different example. So if you guys would flip over to number 2, and let's see what this one is. This one will be a little bit more challenging on C. I want you to do as much of A and B as you can without a calculator. It'll challenge you to remember your unit circle a little bit. I know, that might be inappropriate language this time of the morning, but that's how it goes. All right, so this time your function is g of x equals sine of 2x. Please note that that is a composite function. It'll make a difference as you go through this. Part A, find the equation of the tangent line at that point of tangency. Part B, approximate g of 2.1. And somewhere in there, the calculator will come into play, and I'm okay with that. But then C is really the new thing. Is your approximation too high or too low? And why? Hey, walking around glancing over shoulders, I saw the vast majority of you had this part right. You wrote g prime of x is equal to 2 cosine of 2x. So you're seeing the chain rule. Great. It's awesome. It's easy. Sometimes on these examples did not see that sort of thing, but you saw it, so that's awesome. Of course, this is going to be the slope of the tangent line. At any point, I don't really care about the slope of the tangent line. At any point, I want to know what's going on at my point of tangency. So I plug in 5 pi over 8, and I get 2 cosine of the 8 and the 2 cancel to give me a 5 pi over 4. And that means that g prime of 5 pi over 8 equals negative root 2, right? Because the 2's would cancel when you 2 times negative root 2 over 2. Hey, so guys, any questions on finding the slope of the tangent line at that point? I did skip a couple of steps. Well, sort of. I canceled the 8 and the 2. But otherwise, your unit circle's got to be rock solid. Guys are you guys working on A or B over there? Nick and Santi? Working on A? Any questions? You guys agree with my slope? Yes. Okay, cool. I just want to make sure we're in good shape. Okay, so here it is. And of course, this is really plus a positive.
Where would we be allowed to use it later on?
Part B, yeah, I think it probably makes
Part C.
sense. It's part C.
I think you don't necessarily need to.
You don't need to.
Way easier if
We'll try it without.
then you can pick any to test out.
Right. Otherwise, you got to pick out unit circle stuff. Agreed. So, Santi, Maddie, are you guys doing okay? I want to make sure that I'm not going too fast. Are you sure? Maddie, are you okay?
Well, for myself, I just got -1 over
Yeah, I got the same thing.
Because we did the
Yeah.
40%.
So I'll show you. So if you wrote it like this, you'd say equals 2 times -1 over root 2, right? That's what you're saying? Okay, so this gives you -2 over root 2. So all I did is I used the rationalized version of this. So like if you were telling me, like Maddie, if you and I got into an argument and I said, hey, I think the slope is -root 2, and you're like, no, I think it's that. We're being really silly because we actually have the exact same thing.
So does it matter?
No, it doesn't matter at all. It's same numerically. Because if you rationalize this, that thing you learned way back, of course you can see that this ends up being -2 root 2 over 2, and the 2's would then cancel, giving you -root 2. So whether you do the whole unit circle routine or the triangle thing, if you do it right, you should get the same number. Does that clear it up okay? Okay, awesome. So then I'm hoping that B would go pretty smoothly from here. B, I think, as was asked, I think we just use the calculator. It'd be y plus root 2 over 2 equals -root 2 times, here's where it is, right? 2.1 minus 5 pi over 8. I'm not going to expect you just to like whip that out real quick and be like, oh, of course, it's this or that, right? Calculator time probably. Question, Heather?
For C, we have to test it with a number because we don't know for sure. Never mind.
You're going to have to do a little testing.
Yeah.
Agreed.
But then on
Agreed.
the one before, we didn't have to actually like plug in a number
Because G
of
double
the, like,
prime,
multiplicity and stuff.
well, just because G double prime was always negative.
Yeah, because x cubed will always be positive.
Like if you plug in a positive, which that's all you can do, you'll get a positive. And you square root that, you'll get a positive. That's not going to be the case on this one.
Right.
Yeah.
Okay, thank you.
Yep. Hey, could I just get a quick number on this one? What does y equal when you add the root or subtract the root 2 over 2 over and all that stuff? Just a decimal approximation.
-0.900.
Okay. You guys all agree with that? All right. So you guys want to try to tackle C a little bit? Okay. C is a little bit tougher. I think our class ends at 25, so I'll give you a little bit of room here. So take a minute to do. Anna?
interval because 5, 5, or 8, and then 2.1's from here, right?
This should be a 2x, right?
Yeah, right.
That's gonna change a little bit what your, how your answer
Put that in here.
Because you'll have to divide by 2.
Right. And then
You
this
just
one,
have,
if you
like,
bring it
once you
over,
do your inverse
Oh, do you just
sine
want
of
to
both
do
sides,
it?
do this,
I-
once you've done that,
No,
then you
that's
just
not-
divide
I don't
everything
know if
through by
that's
2
I'm guessing right
to
now.
get,
Okay, okay, no, I see it.
those numbers, okay.
I also just multiply by
Yes, ma'am?
How do we know what number we should test?
Well, no, we just.
So, of course, I think it should be -4 sine of 2x, because you already had that 2 hanging out there. So, what we'll talk about here in a second is, in number 1, g double prime was negative, regardless of what you plugged in from the domain, right? Here, as you, I'm sure you can tell, sine is constantly going from concave up to concave down and back and forth, right? And so we need to decide, all right, well, since g is constantly changing from concave up to down and down to up, wouldn't g double prime be constantly changing from positive to negative to positive to negative, et cetera, et cetera?
Yeah.
So if I'm trying to figure out where g prime is positive or where g prime is negative and where it's switching back and forth, what number might be a hint to help me with that?
Yeah.
So I would set your g double prime equal to 0. That's going to allow you to set up some realistic intervals, only one of which you'll need to test.
Got it.
You can test all of the ones you want, but there's really only one you have to test.
Okay, thank you.
Yep. It should be 4, right? So you already have this 2 here.
Yeah.
So when you do another chain rule, another 2 will come out.
I'm gonna get rid of this. Derive it. The derivative is 2.
The derivative of a constant multiple is not 0.
So you're saying that on all the positives.
If that were true, then g double prime would be 0. Right, so there's the difference between the derivative of a constant multiple. So we talked about this before, so we can remember. So if I told you
That's,
that g of x was equal to 2 sine of x, and f of x is equal to 2 plus sine of x. You see how the 2 is used differently? One on the left is constant, so the derivative would just be 2. Oh,
Because the points are
be 2 cosine. On the right, the derivative of 2 as a term is just 0.
I remember
I mean,
it's
cosine.
you say
Cosine.
cosine, like it's cosine.
Yeah.
So x is
So that's why it's
That was like a 5-shot streak that I just lost.
What are you figuring out when cosine is 0?
Hey, Anna, I'll try to answer your questions as we roll here. We got about 5 minutes. I want to make sure we get done. Hey guys, listen carefully. I hope this reasoning makes sense to you.
What?
Guys, same sort of reasoning here. We're going to use the second derivative to figure this out. And so here's my first derivative. It is from up above. It's f prime equals 2 cosine of 2x. So it's still composite, but the derivative of cosine is negative sine, right? So f double prime would equal negative 2 sine of 2x times another 2 from the chain rule. So f double prime ultimately would equal negative 4 sine of 2x. And this is where this one is a little bit different than what we did in number 1. Because in number 1, we were able to reasonably conclude that f double prime is always negative, right? Regardless of input from the domain. Here, if you're honest about this, doesn't, like the original graph is a sine graph, doesn't a sine graph just constantly wave? And doesn't a sine graph constantly go from concave up to concave down to concave up to concave down, so on and so forth? So it's not going to be nearly as cut and dried as we had in number 1, where you could just say, hey, f double prime is always negative, and make a conclusion, you're done. So because f is constantly changing from concave up to down and back and forth, couldn't you say then that f double prime is constantly changing from positive to negative to positive to negative to positive, et cetera, et cetera? Okay? So if I'm trying to figure out where f double prime is positive or negative, what is the one number that might give me a clue about that? 0. That's assuming we have a continuous graph, which we do. 0 is going to tell us where f double prime perhaps changed signs. So what I'm going to do here is set this equal to 0. This is where a little bit of trigonometry in the old unit circle routine comes into play again. I would divide through by negative 4, so I'd get sine of 2x is equal to 0. And then I'd come back up over here and say, all right, well, if sine of 2x equals 0, 2x is equal to the inverse sine of 0. And what's the inverse sine of 0? 0 and pi and 2 pi, right? They just keeps going, doesn't it? So I could say 2x equals 0, pi, 2 pi, 3 pi, ... Just keeps going. I don't know how far I need to go, because all I really need is the right interval for me. I don't know how far I need to go. I do need to divide by 2. So x is equal to 0, pi over 2, pi, 3 pi over 2, comma, ... Could keep going. So I've created a bunch of intervals here, right? The first interval would be from 0 to pi over 2. The next one would be from pi over 2 to pi. The next one would be from pi to 3 pi over 2, so on and so forth. So the question is, my 2 points, my point of tangency, which is 5 pi over 8, and my approximation point, which is 2.1, do both of those numbers fit within any of those intervals?
Yeah. Pi over 2.
Between pi over 2 and pi. Now, you could use the calculator to approximate some stuff and be like, oh, cool, they actually do fit there. But this is the interval. You guys are right. It fits, those two numbers fit between pi over 2 and pi. So all I have to do now is basically see, well, is f double prime positive or negative between pi over 2 and pi? What might be a good approximation number to use, or like a good test value to see what happens within that interval? What's between pi over 2 and pi? Yeah, but it's going to be 5 pi over 8 would be good. 2.1 is going to be awkward without a calculator. If you do have a calculator, you could just use one of the two numbers. Sure. 3 pi over 4 is right in the, or 3 pi over 2, excuse me, is right in the middle, isn't it? Or 3 pi over 4 is in the middle. There we go. Yes. So I could do that. I could do one of the numbers, whatever you want to say. So I'm going to say f double prime of 3 pi over 4. I'll finish it off with a unit circle here. Well, let's see here. That would be sine of 3 pi over 2. And what's the sine of 3 pi over 2? Come on. Sine of 3 pi over 2?
Oh, 0.
No, not 0.
3 pi over 2.
Negative 1. And then negative 1 times negative 4 is positive 4. Oh, yep, it should be. All these should be G's. Just I misspelled G with an F. Thank you. Okay, so that number is positive. So since G double prime is positive, G is concave up, and my approximation is too low. So I can say, because of this reasoning, therefore, my approximation is too low because G double prime is negative on the interval from 2.1 to 5 pi over 8. Something like that. So really, if you think about it,
Wouldn't you, could you also...
darn it. Sorry, I'm trying to rush because I know you guys are at the end. It's positive. Okay, hold on, Anna. Sorry. Your question? Go ahead.
Could your interval be pi over 2 and pi?
So you have to include the interval that mentions the point of tangency and the point that you approximated with. And so I would always default to that. Now that's contained within pi over 2 to pi, but always mention the interval that contains the two key points, right? Point of tangency and point of approximation. So guys, there's a little bit more with these notes. All of it is like relatively optional kind of stuff. We're not going to cover it. I think we're good there. Let's see here. So make sure you got the chapter 4 notes stashed in your bag for tomorrow. We don't quiz on this material until next Monday, I think. So we'll talk about that later. Stu, if you want to hang around for a second, I'd be happy to talk to you about that number 2.
I have English right now.
Okay, sorry. Blame it on
Green off, right?
blame it on KISS.
You have green off.
Blame it on KISS.
Are you going to be here?
That's the question. I don't know. I have to check my calendar. My calendar, you would not believe how full my calendar is getting, my friend. I can't assume.
I was surprised that you were there.
Yeah.